Hello everyone! In this video we start on a new series about classical electrodynamics. As the electromagnetic force is one of the most apparent forces in our everyday life, there will be a lot to discuss. We will talk about magnetism, electricity, and how the two combine as electromagnetism. In this video we start off simple by looking at magnetism. What is it? What is the physical phenomena behind magnetism? In this video we will skip the equations and we will try to visually understand what magnetism is. So I hope you will enjoy learning about the different types of magnetism and the physics behind it. In short, magnetism is a particular property of a material, and it is mediated by a magnetic field. Essentially, objects are either repelled or attracted by a magnetic field. However, it can be more complicated as some materials can show different behaviors depending on the situation. A lot of materials appear to be neither repelled or attracted, but actually materials in general are always affected by a magnetic field. Just sometimes you need a very sensitive experiment to measure it. Magnetic objects always have two poles, also called dipoles. In everyday life, we often denote the poles north and south. This is due to the fact that the Earth itself is a big magnet, with poles being near the north and the south pole. Historically, magnets became useful in navigation as compasses, and the compass points towards the magnetic north pole in one end and towards the magnetic south pole in the other. To understand magnetism better, we should consider some basic quantum mechanics and understand how atoms are made. Atoms have a nucleus, and around the nucleus they have electrons. Due to the Pauli exclusion principle and the underlying quantum mechanics, we get that the electrons occupy shells or orbits around the nucleus. These electrons can have two different quantum states, up or down. In the shells, the electron can pair up. In each pair, one electron is up and the other is in the down state. They cannot be the same. Depending on the atom, the electrons manage to pair up, but sometimes there are, for example, an uneven number of electrons, making it impossible for electrons to form a pair. Therefore, we can have atoms with so-called unpaired electrons. It turns out that the difference between having paired or unpaired electrons play a role in the magnetic characteristics of atoms. This is because the electrons have what we call spin magnetic moments. It's like small magnets. We will now take a look at some important cases of magnetism. If nothing else, a material is diamagnetic. This means that the material is very slightly repelled by a magnet. In general, diamagnetic materials have paired electrons, and because the electrons must be opposite in spin, the spin magnetic moment cancels out, leaving only a weak diamagnetic property from orbital motion. So only materials that have no significant ferromagnetic or other magnetic behavior can be observed as diamagnetic. So to measure this repulsion, you need a highly sensitive measurement. The cool thing about true diamagnetic materials is that they can levitate due to the repulsion of magnetic fields. An example of this is superconductors. And this is actually how maglev trains work. They use superconductors to make the train levitate, and this means that there are no spinning wheels. This dramatically reduces the resistance working against the train, such as resistance in the drivetrain. Thus, the only thing stopping the train from going faster is air resistance, just like airplanes. Currently, the maglev train speed record is a bit over 600 km per hour. Another phenomenon is paramagnetism, which occurs when unpaired electrons align in a material due to an external magnetic field. In this case, unpaired electrons of each atom align with the magnetic field, making the material magnetic and attracted to a magnetic field. In general, magnetization occurs when unpaired electrons are aligned, thus the bulk magnetic moment becomes significant and the material becomes magnetic. There are, however, other forces working against this. Temperature causes random fluctuations that ruin the alignment. This is why paramagnetic materials lose their magnetization when you remove the magnetic field. The electron dipole moment becomes random again and the material is no longer magnetic. Some materials like iron, nickel and cobalt have another special property called ferromagnetism. In general, these materials have unpaired electrons like paramagnets, but it turns out that these materials keep their magnetization after you remove the magnetic field. It turns out that for ferromagnetic materials, it is more energetically favorable that all the atoms orient themselves parallel to each other. So if you just get them aligned once with a magnetic field, they'll remain aligned and you just get a permanent magnet. Such materials still feel thermal fluctuations and it is possible to destroy the magnetization if you heat the material above its Curie temperature, which is the temperature at which a ferromagnet loses its magnetization, because the fluctuation overpowers the energy benefits of being aligned. So this permanent magnetization is not completely permanent, so to say. There are many other types of magnetic characteristics one can consider, but let's just go through two more complex possibilities, like AntiFerromagnetism and Ferromagnetism. These are both ordered state, so no random alignment like in a diamagnetic state. The antiferromagnetic state is, however, similar to the diamagnetic state because the net magnetism is zero as the dipoles cancel out each other, as the neighbor dipole always have the opposite orientation. Above a certain temperature, antiferromagnetic materials typically become paramagnetic. Ferromagnetism is similar and occurs in materials with different atoms with opposing magnetic moment. Ferromagnetic materials are, however, still attracted to magnetic fields like ferromagnets. This is, however, not the case for antiferromagnets, which are magnetically neutral. I hope you liked this overview of magnetic properties of materials. Note that magnetic fields always have dipoles. Thus, that means that there is a north and a south pole always. You cannot have something which is just a north pole or just a south pole. At least we haven't discovered such monopoles. As we will see in the next video about electricity, it is possible to have objects that have just a positive charge or just a negative charge. Thus we have electric monopoles. This is one of the differences between electric and magnetic fields. I hope you will find this new series interesting and that you might learn something new. If you have any topic you would like to see covered, let me know in the comment section together with other feedback. As always, please like and subscribe if you want more such videos, as it helps promoting the videos. I hope to see you in the next one. Stay tuned for the next video.